here's hopefully some revision on fractions. So a fraction is made up of two elements. These are a numerator and a denominator. And when we actually turn that into doing a sum, into doing the calculation, those are called a dividend, and the thing we divide a dividend by is called a divisor. The result of that is in a quotient. But the most important ones for today are the numerator on top of the fraction and the denominator on the bottom. Now when we add or subtract fractions, we have to have a common denominator. I know there's been a few bits of confusion around that in terms of whether it's divide or multiply. No. When we add or subtract fractions, the only way we can do that is with a common denominator, so they're out of the same proportion things. For multiplication, well, that's actually the easiest one. We just multiply a numerator by a numerator and a denominator by a denominator. So when we're multiplying two fractions together, multiply the top two numbers together, multiply the bottom two numbers, or in this case, as we're going to move on to today, letters together, and that's your multiplication. Division works very similarly, but if we divide one fraction by another fraction, we flip the second fraction, that divisor fraction, the fraction we are dividing the first fraction by. We flip it, and then we do a multiplication instead. So, here are some examples of that. Right, addition and subtraction, again, we need a common denominator. So, for example, here I have an equation. Well, I don't actually have an expression. Okay, 2x over 5x plus 4 over x. Now, I can't do anything with those until they have a common denominator, because the 2x is a description of out of 5x, and the 4x is a description out of x. So I'm going to get them to have a common denominator, and I'm going to do that by multiplying the fraction on the right by 5. I'm going to multiply top and bottom by 5. So that's going to give me 2x over 5x plus 5 times 4 over 5 times x. That gives me 2x over 5x plus 20 over 5x. And now I can add those two top pieces together and get 2x plus 20 all over 5x. Another example, x over xy plus x over y. Again, I can't do anything with these until I have a common denominator. So here, I've multiplied the fraction on the right, top and bottom, by x. Again, you have to multiply both the top and the bottom, both the numerator and the denominator, by the same thing. Otherwise, the proportions change and you've just changed the meaning of that fraction. It won't equal the same thing when you multiply it out. So I've multiplied the second fraction there, x over y, by x over x. Multiply top and bottom by x, and that's going to give me then x over x plus y plus x squared over xy equals x plus x squared all over xy. Now, multiplication. Again, in this case, what we do is we multiply the numerator by the numerator and the denominator by the denominator. This is actually the most easy, I think, operation with fractions. So, for example, here, if I want to multiply x over y by x over y, I just multiply the two together. X times x on the top gives me x squared, y times y on the bottom gives me y squared. So my final fraction is x squared over y squared. I want to multiply x over y by y over x. I can say actually that's the same as x times y over x times y. And of course, anything divided by itself is 1. So that's what I've got, equals 1. A slightly more complicated one now. X minus 1 over x minus 2 multiplied by x over y. I multiply the numerators together. I put x on the outside of that bracket. So I've got x, open bracket, x minus 1, close bracket, all over y on the outside of the brackets, x minus 2 on the inside of the bracket. And they're going to multiply both of those out. And that's going to give me x squared minus x on the top here, and at the bottom I multiply out this process to give me xy minus 2y. And then I'm really stuck. I can't do much else. I could, if I wanted to, split out this fraction and say it's x squared over xy minus 2y minus x over xy minus 2y, but it doesn't really help me do anything else at this point. But just to make the point that we can do that. We can split the numerator, keeping the denominator the same. It doesn't change the meaning of that information, and if you doubt that, put some numbers in there. Put numbers into x and y and see what happens. But one thing we can't do is ever split the denominator. So make sure you can realize that you can split that numerator up. So I've still got x squared minus x, and as long as I keep them over the same denominator, I don't change the meaning of that information. So a couple of examples of division. Again, we're going to use the same operation we use for multiplication, but first we have to flip the divisor fraction, the second fraction. So in this case, I've got x over y divided by y over x. I'm going to flip the second fraction, that's the fraction on the bottom there, the divisor, and that's going to give me x over y times x over y, which of course, just as we've just done, is going to equal x squared over y squared. Slightly more complicated one. X plus 1 over x plus 2 divided by x plus 1 over x plus 2. That second fraction, I'm going to flip it, and we're going to change the sum to a multiply. So this becomes x plus 1 over x plus 2 multiplied by x plus 2 over x plus 1. And that gives us this final result here. X plus 1, x plus 2 over x plus 2, x plus 1. Now I could at this point multiply out the brackets if I wanted to, but I've noticed something. Actually, we've got common things on top and bottom, and they cancel. Because x plus 1 divided by x plus 1 is 1, anything divided by itself is 1, I can eliminate that and give myself x plus 2 over x plus 2. But that's still two common elements on top and bottom. X plus 2 divided by x plus 2 is 1, because anything divided by itself is 1. So always keep a watch out for those, because they can be really handy to eliminate unnecessary sums. There is something else I wanted to remind you of for the fractions that I haven't gone over yet, and that's this. As with the linear terms, when we've looked at applying a power to things inside brackets, we said that we have to apply a power to all of the elements inside the bracket. So if we had AB inside brackets squared on the outside of the brackets, that's the same as A squared, B squared. We have to square everything inside the bracket to get rid of the brackets. The same is true for fractions. Here I have an example. A over B in brackets to the power of x is the same as a to the power of x over b to the power of x. The only way I can get rid of those brackets is to make sure I apply the power x to every element inside the bracket. So for example, I've got some example here with numbers. I've got 4 over 2, all squared, so 4 over 2 inside the bracket, squared on the outside. And I'm saying that that is the same as 4 squared over 2 squared. And just to show that's true, I've developed that sum. So 4 over 2 is 2 squared. And on the right-hand side, 4 squared is 16. Divided by 2 squared is 4. And both of those, 2 squared and 16 over 4, is going to give me the same quotient, answer 4. The other section of today's mini lecture is transposition. This is about rearranging and changing formulae, changing equations. But we have to make sure that when we're changing them, we aren't changing the meaning. We have to make sure that they're still true to the original formula or expression we were first given. That means we do that by applying the same process to both sides of the equation every time. So we can add the same quantity to both sides, we can subtract the same quantity from both sides, we can multiply both sides by the same quantity, we can divide both sides by the same quantity, and we can square or apply a power, again, to both sides. But we always have to do both sides of that equation. So here's a simple example. I've got the equation x equals 5y plus 5. If I want to get y by itself, I want to do what's called solving for y. I want to solve for y and get y by itself. Firstly, I'm going to take 5 from both sides. So x minus 5 on the left, 5y plus 5 minus 5 on the right. We can then get rid of those 5s on the right-hand side here. Plus 5 minus 5, and that gives us x minus 5 equals 5y. But to get the y as just the y by itself, I'm now going to have to divide both sides by 5. So x minus 5 over 5 is the same as 5y over 5. And that's going to give me y equals x over 5 minus 5 over 5, which means y equals x over 5 minus 1. If you just want to, with the fractions there, I'm just doing exactly the opposite of what we did slightly earlier, and I've just put some numbers here to show that that is true. So if you're not sure about that working, have a look at those numbers, because it shows that that split of that fraction where I've kept the denominator the same, but I've split up the numerators, works. And I've done that because I can see that 5 divided by 5 is going to be 1, and that's going to give me an easier piece of information to deal with. It's going to give me less information, which is part of this simplifying process. So here's a simple example of transposition, which you've probably already used, and that's why I'm using it. I know you're looking at mole calculations as part of your lab work, so I'm using this as an example here. I've got the equation n equals small m over big M, where n is the number of moles, little m is the mass in grams, and m is the relative molecular mass. So I want to rearrange to enable calculation of mass. For example, or i.e., I want to solve for little m. So how do I do that? Well, I start with n equals m over big M. I'm now going to multiply both sides by the big M, because I want the little m by itself. So I have n times big M on the left, and m over big M multiplied by big M on the right. The ones on the right cancel. M over m is 1, and that means that I have little m equals n times big M. Here's a slightly different example. This is one from physics, and it's the equation for calculation of kinetic energy of an object. E equals half mv squared. So where E is the kinetic energy in joules, m is mass in grams, and v is the velocity in meters per second. So now I'm going to ask myself to rearrange to enable calculation of velocity, i.e. we're going to solve for v, solve the equation for v. So again, I'm going to start with E equals half mv squared. This time I'm going to multiply both sides by 2 to get rid of that half, because half is a slightly awkward number to be mucking around with. Multiply both sides by 2, and so I'm going to get 2e on the left, and the half disappears on the right, because the half multiplied by 2 is 1. I'm then going to divide both sides by that little m, because I know I want the v to be as lonely as possible, so I can work with it and get v by itself in the end. So I get 2e over m on the left and mv squared over m on the right. Those m's cancel, and we end up with 2e over m equals v squared. Now, you'll notice this isn't v, it's v squared, and I want to solve for v. So I have to square root both sides. There's a couple ways I can write that. I can write it like this. So I can say the square root of 2e over m equals the square root of v squared. Squaring square rooting anything that's squared obviously just gives us that value, v. So, v equals the square root of 2e divided by m. I could also, of course, have written the square root as to the power of a half on the outside of brackets. So don't forget that that is also a way that we write square root. There's a few things to learn about powers, also called indices. The first thing is that we write them like this. It's x to the n. X represents a number, n represents another number, and basically that notation means that it's the number x multiplied by itself n number of times. So for example here, you can see 3 to the power of 4 is 3 multiplied by itself 4 times. So 3 times 3 times 3 times 3, which is 81. There are a couple of other things you need to be aware of. Some little tricks we use. This is useful partly for numbers, but it's certainly very useful later on, and we'll look at it again when we look at algebra. We like to write a rule that is x to the power of m multiplied by x to the power of n is the same as x to the power of m plus n. Now again, we've got an example here, just to show that that's true. 3 squared, 3 to the power of 2, multiplied by 3 to the power of 3 is the same as saying 3 to the power of 5, so that's 3 times 3 times 3 times 3 times 3, which is 243. And you can check that out yourselves just to check it. The next rule I've got on here is to do with a minus n. So, x to the power of minus n is the same as saying 1 over x to the power of n. So again, the example we've given is 3 to the power of minus 4 is exactly the same as saying 1 divided by or over 3 to the power of 4, which equals 1 over 81, and that's 0.0123. Some other rules. This one's really quite similar to the other, but it's related this time to dividing powers by others. So, the rule is x to the power of m divided by x to the power of n is the same as or equals x to the power of m take away n. So again, the example is 3 to the power of 4 divided by 3 to the power of 2, and believe it or not, here we calculate it, 3 to the power of 4 minus 2, which equals 3 squared. And you can calculate that on your calculator to see if it's true. There are a couple of special cases. Here, x to the power of 1 equals x. Any number to the power of 1 is just itself. 5 to the power of 1 is 5. 7 to the power of 1 is 7. Anything at all. Again, try it on your calculators. The other special case is any number to the power of 0 equals 1. And that's quite useful if you're taking things away and end up with a 0 up here, for example. The final rule that you need to be aware of is x to the power of 1 over n is the nth root of x equals y. In other words, y to the power of n equals x, then x to the power of 1 over n equals y. again, the best way to test this out is to plug some numbers in and see how it works. Here we've got an example, 81 to the power of a half. A half is interesting. 81 to the power of half is the same as saying square root. That's a third or a root. They mean the same thing. And of course, they both equal 9. Again, you can try this out on your calculators. And just to prove it so, the rule above, 9 times 9, or 9 squared, is 81. So that does work both ways. Same here, 16 to the power of a quarter is 2. 2 to the power of 4, or 2 times 2 times 2 times 2, equals 16. Just keep putting some numbers in and see what happens, and you'll see it's true. So now we're going to talk prime numbers. Hopefully you've come across these in the past. A prime number is a number that can only be divided by itself and the number 1 to make whole numbers. Examples are on the board here, 2, 3, 7, 13, 19, anything that can't be divided cleanly, we'd say, into an integer or a whole number, unless it's being divided by 1 or itself. Now, using these, we can do something called factorizing, or factorization. Now, it says that factorization means write as a product. Now, I think you would have read last week that a product is the product of a multiplication. So, when we prime factorize or factorize things, we're going to split them up into the prime numbers that we multiply to get to that final number. So, I'll show you some examples. Here, we've been asked to factorize 84. 84 is clearly even, so I know I can divide it by 2. If I do that, I'm going to get 42. 42 is also even, so I know I can divide it by 2 again, giving 21. 21, I know my 3 times tables is divisible by 3, and that's 7, which is also a prime number. So to fully factorize or prime factorize 84, what I get is 2 times 2 times 3 times 7, which we can also write as 2 squared times 3 times 7. And it really does help here to know your times tables. So, there are some tricks to working out which factor you can divide into those numbers. The first, as I said, is it even? If it's an even number, you can divide it by 2. That's an easy one. The second, if it ends in a 5 or a 0, you can divide it by 5. So 5 is definitely a factor. The third rule is, do all the individual digits in the number, when you add them up, make a number that's divisible by 3. If that's true, then the factor is 3. I can show you an example in a sec. And the last rule that I'm going to tell you about is one for 7. With 7, it's slightly complicated. You take the last digit of the number, you double it, and then you take it away from the rest of the number that's left without that final digit. And if the answer is divisible by 7, and that includes 0, then that means that you actually have a number that 7 is a factor of. I'll give you some examples. So here I've got the number 18,954. If I add each of those digits up, 1 plus 8 plus 9 plus 5 plus 4, I get 27. 27 is divisible by 3, it's in the 3 times tables. So that means 3 is definitely a factor, and I can divide that by 3. I've also gone here with 259. Now this is the rule of the 7s. The way we do it to work out if 7 is a factor, we take that last digit, the number 9, and we multiply it by 2. And we take it away from the rest of the number, which in this case is 25. So 25 minus 2 times 9, which is 25 minus 18, and that equals 7. 7 is of course divisible by 7, so that tells us that 7 is a factor of 259. But what about when we get higher than that? What about, we can work out things like 9 or 7. I'm sorry, not 9. 9 is not a prime number. We can work out 3 or 7 or 2. That's quite easy, because those times tables are quite easy. But once we get to larger numbers, well, we have to look quite differently to see if we can work out if there are larger prime factors. Here I've done a table for you where I've got the product of each of the numbers in the top row and the side column. So, for example, here 121 is 11 times 11. Down here, 437 is 23 times 19. And you can use that then to look at the numbers you're left with if you can't see an obvious factor. Of course, in that scenario, you can also use a calculator as well to try and work out what the factors might be. So, the last things we're going to discuss in this mini lecture are highest common factors and lowest common multiples. So, here's the definition of the highest common factor, which we'll also call the HCF. The highest common factor is the largest number that is a factor of a set of numbers. So, let me show you what that means. Here, I've been asked to find the highest common factor and the lowest common multiple of 1020, 2652, and 7854. I'm going to start with the highest common factor. The first thing you have to do is take all of these items down to their primes, prime factors. So I factorized each of these numbers out. So the first one, 1020, I know I can divide by 2 because it's even. 510 I can divide by 2 because it's even. Then I can divide by 3, and etc., and etc. So having done that, I end up with 1020 is the same as 2 times 2 times 3 times 5 times 17. I then followed the same processes for 2652 and 7854. You'll get a chance to do this in your tutorials. To find the highest common factor, or HCF, what we do is we look at which factors are common to all 3 numbers. So here I've highlighted them. In all 3 of these numbers, when we've broken them down into their prime factors, we can see they all have 2, 3, and 17. You might ask why we haven't got 2 2s highlighted. Well, this number at the bottom doesn't have 2 2s in it. If it did, then we would certainly have that in there as well. But in this case, the only 3 common numbers between each of these things are 2, 3, and 17. That means that we calculate the highest common factor by multiplying those together. 2 times 3 times 17. That is the highest common factor. Have a look in your books, have a go at this. There's lots of exercises to get your teeth into in the core reading and exercises. The final thing we're going to look at is the lowest common multiple. Again, the lowest common multiple for a set of numbers is the smallest number into which all of them will divide. So this time we're not going smaller, we're going bigger. So to find the lowest common multiple, we have to again factorize each set. We have to take the highest number of each number of factors, and then we work it out using that, and I'll show you here. Here's a nice simple example at the bottom. I've factorized 2, 4, and 5. Obviously 2 is already a prime number, 5 is already a prime number, 4 isn't. 4, when you prime factorize it, is 2 times 2. So the factors here are 2 and 5. It doesn't matter on the number at the moment. Factors are 2 and 5. But now we have to count. we have to look at what's the highest number of 2's that are multiplied in any single sum there. And if I look, well, that would be 2 2's. 2 2's is the highest number of 2's we multiply at any moment in that factorisation. In terms of 5's, well, actually, the highest number is 1 because it's only in 5. To calculate the lowest common multiple, we therefore take 2 2's and 1 5 and multiply them together. 2 times 2 times 5, giving the lowest common multiple 20. 20 is the lowest number that number 2, number 4 and number 5 can be divided into. Here's an example for the numbers we looked at earlier. The lowest common multiple of 1020, 2652 and 7854. Again, I've taken that factorisation that I did earlier. Up here you can see them, so 1020 is again 2 to the power of 2, or 2 times 2, times 3, times 5, times 17, and so on. Here, there's quite a few factors. There's 2, there's 3, there's 5, there's 7, there's 11, there's 13, and there's 17. And so this time I have to again look at what's the maximum number used at any time. Well, the maximum number of 2's used is 2. It's used in both 1020 and 2652's factorisation, but I've only highlighted one of them. 3 is used just once in all of them. 5 is used just once. 7 is used once. 11 is used once. 13 is used once. And 17 is used once. Now obviously it's in all three things, but the highest number that are used in any of those sums is 1 for everything but 2. So I calculate the lowest common multiple by multiplying 2 times 2 times 3 times 5 times 7 times 11 times 13 times 17, which gives us 1,021,020. And that's how you do one of the more complex finding of highest common factor and lowest common multiple. So first I need you to be familiar with a couple of terms that we're going to be using, and I'm going to be using these all the way through this lecture, so make sure you understand them now. If you need to pause it, if you need to remember them, make sure you do. So fraction, we have an example here. We've got 3 out of 4. Just here. This is an example of a fraction. It has 2 parts, a number at the top and a number at the bottom usually, although there are other kinds of fractions which we'll go through later. But generally, it will have a numerator, which is the number at the top, and a denominator, which is the number at the bottom. Make sure you're familiar with those terms. So, for example, in our fraction, in our 3 over 4, or 3 quarters, or 3 out of 4, we have 3 is the numerator, and 4 is the denominator. Now this is, interestingly, it's also the same as saying 3 divided by 4. So obviously we can calculate this out. And if we actually do that calculation, then we change the terms. The terms would be the dividend, in this case 3 would be the dividend, and 4 would be the divisor. The result of that calculation would be this. 0.75, and that's what we call the quotient. The result of the calculation from a fraction is the quotient. So there are different kinds of fractions. The fraction that you'll most often have seen probably before this is called a proper fraction. A proper fraction is where the numerator, here, number 5 in this case, the numerator is less than the denominator, or the 6. So where the numerator is smaller than the denominator, that's what we call a proper fraction. An improper fraction is where the numerator is bigger or greater than the denominator, such as this one, 6 over 5. 6, the numerator much bigger, well, not much bigger, a bit bigger than the denominator, and that makes this an improper fraction. Now, we can turn an improper fraction into a mixed fraction. And I've got an example here. So here I have 6 over 5, or 6/5, and I know that 6/5 is the same as saying 5/5 plus 1/5. The same as saying 5 out of 5 plus 1 out of 5. And that can be turned into 1 and 1/5, because of course 5 divided by 5 is 1. Now, quite often in science and engineering, we need to be able to add or subtract fractions. In order to be able to do that, we have to get the denominator the same. So you can't add 1 over 2 to 3 over 5 just by some quick method. We have to get the denominator the same. Now, just to remind you that different fractions can be expressed in many different ways. So, for example, here we have 1 over 2, or 1/2, and that is actually the same as 2 over 4, which is the same as 3 over 6. You put those things into your calculator, you're going to get the same result. The quotient will be the same. But when we want to add or subtract different fractions, we need to make sure that the denominator is the same, and that's what we call a common denominator. Now, to give you a little bit of insight based on what we did a couple of weeks ago, the lowest common denominator is the lowest common multiple of the denominators of all the fractions. So, if you need to remind yourself of what that is, if you need to remind yourself what the lowest common multiple is, you should go back and have a look at week 1. Now, there are a few different ways of looking at this. If you just want to add up a simple fraction to another simple fraction, there's a really simple way that we can do this to find the common denominator. For example, here I have 1 over 4 plus 2 over 3. I need to find a common denominator, and the simplest way to do that is to multiply 4 by 3 to get 12. The reason that works is because I know I can turn the fraction into a different fraction, but with the same information, and I'll explain what I mean by that. We can change the denominator, but if we do that, we have to keep the fraction the same. It needs to have the same information in it, and that means that when you put it into a calculator, you need to get the same quotient out. So what we do is we multiply both top and bottom by the same number. So, first we were dealing with 1 over 4, a quarter, here. In this case, I want to multiply 4 by 3 so that I have a common denominator, 12. But to keep that fraction the same, I have to multiply the top by the same number. So I've got 1 times 3 divided by 4 times 3. Then I'm going to do the same for 2/3 here. But this time, I'm going to multiply both top and bottom by 4, the denominator of the other fraction. That means I end up with 2 new fractions, but they do, believe me, have the same information in them. 3 over 12 plus 8 over 12. Now, we can add those up really easily by just adding the numerators together. 3 plus 8 is 11, so 3 over 12, or 3/12, plus 8/12 equals 11/12. But what about if we have lots of fractions that we have to add or subtract together? Well, in this case, we can use what we learned about the lowest common multiple. Again, if you can't remember what that is, please go back to week 1 and have a look at it. In this case, we have a sum, which is 1 over 2 plus 2 over 5 minus 3 over 8. Well, how do we even start to approach this? We could do it the way I've just shown you. We could just deal with the first 2 fractions, change to the same denominator, in that case would be 10 using that method. And then once we had a new fraction for those first 2, then we could do it for the second fraction. But there is a quicker way, and that is to use the lowest common multiple. Just to remind you, to get the lowest common multiple, we have to get down to the factors of those individual numbers and then multiply them together to find our lowest common multiple. Now in this case, if we factorise 2, it's just 2, it's a prime number. And the same for 5. 8 is actually the only one we can prime factorise. And if we do that, we actually discover that we can divide it by 2, which would be 2 times 4, which of course is 2 times 2. So, factorised, apologies for that, it's difficult to write on this, is 2 times 2 times 2. So our lowest common multiple is going to involve the factors 2 and 5. And if you calculate that out, it's going to be 2 times 2 times 2 times 5, which is 40. So, I've determined that the lowest common multiple of these 3 denominators is 40. Well, now I have to convert those fractions. So how do I do that? Well, I do exactly the same thing. I have to look at how I keep that fraction the same. So if I'm converting 2 at the bottom here as the denominator of 1/2 to 40, how do I do that? Well, I've multiplied 2 by 20 times. So I have to do the same to the top of the fraction here. So 1 over 2 becomes 20 over 40. 5, the denominator of the second fraction, goes into 40 8 times. So I have to multiply the top of that fraction by 8 as well, and that gives us 16 over 40. For the third fraction, again, 8 goes into 40 5 times, so I have to multiply both top and bottom by 5, giving 15 over 40. Now you can see here that I can write it in this fraction either with separate fractions over the same denominator but separated out, or then on the next line I can actually combine these and have 20 plus 16 minus 15 all over 40. Again, if you want to check that with your calculator, you can, but that means the same thing. And again, it's reducing the amount of information we have to do. And if we want to calculate it out, it's reducing the amount of processes we have to follow. So, if I do 20 plus 16 minus 15, that's 20 plus 1, and that gives an answer of 21 over 40. Thankfully, multiplication of fractions is a lot easier. I do admit that adding and subtracting fractions together is a bit clunky. You need to practice that. Multiplication is actually a much simpler process. All we do to multiply fractions together is we multiply all of the numerators together up here, and we multiply all of the denominators together down here. So in this case, we have 1/2 multiplied by 2/5 multiplied by 3/8. At the top, we have 1, 2, and 3. We multiply all of those together, 1 times 2 times 3, which gives us 6. Then we do the same for the denominators to give us our new denominator. 2 times 5 times 8 at the bottom here, which gives us 80.
that gives us a fraction 6/80. Now, you may well have noticed that that fraction can be what we call simplified. Simplifying means removing as much information as possible without changing the meaning. It means making things simpler. So here we want to reduce the numbers to the lowest possible value we can. It's a little bit like when we looked at factorising, but here, as long as we divide both top and bottom of the fraction by the numerator, both the top and the bottom of the fraction, the numerator and the denominator by the same thing, we can forget the information because the result or the quotient of that would still be the same. So here you can see we have 6/80, which has been simplified by dividing both top and bottom by 2 to 3/40. It's good practice to always take a fraction down to the lowest numbers we can. So if you can factorise those numbers and reduce it down, you should. And just to show you why that works, we can actually write 3 as a fraction. We could call it 3 divided by 1. And if we do that, then we have 1 times 3 at the top and 4 times 1 at the bottom. So it does still follow our multiplication rule, if you know that 3 is the same as 3/1. But don't get too mixed up on it. Just try and remember that if it's a whole number, you can just multiply the top number, the numerator, by that number. Okay, division. Actually, this is also pretty simple, but there's a trick to it. You have to know that dividing by a fraction is the same as multiplying by the flipped or inverted fraction. Again, you'll have to try this on your calculator if you want to understand it or see it, but I can give you an example here. For example, I have a sum 2/5 divided by 3/8. Now, in order to calculate that or to simplify it, I'm going to flip the 3/8 to 8/3 and change the sign from a divide to a multiply. So my new calculation is 2/5 multiplied by 8/3. That's a top-heavy or improper fraction. Now we just follow the same rule we followed for the other multiplication sums. So we multiply the numerators together, so we get 2 times 8 at the top. We multiply the denominators together, we get 5 times 3 at the bottom, which is 15. So we end up with 16/15. Now again, that's an improper fraction, so ideally what we want to do in this case is we can take it to be a mixed fraction of 1 and 1/15. Now this will be coming up again in a few weeks, but I thought we'd take a look at it now very quickly. We can actually apply powers to fractions in the same way we did to whole numbers last week. If you see a power applied to a fraction outside of some brackets like this, then it's really easy to get rid of that, to actually be able to calculate that out. All we do is it's actually the same as saying that we apply the same power to both the numerator and the denominator. Now, you might have to get a bit used to us using letters in place of numbers. In this situation, A represents a number, B represents another number, X represents a third number. Try not to get too confused by that. I'll give you some number examples now. There's another example below. Have a look at that if you like by pausing the video and seeing if you can check it with your calculator. top we have the number 123. Now we can write 123 like this. 1 times 100 plus 2 times 10 plus 3 times 1. Now, it's written in brackets to make it clearer, but obviously after the last couple of weeks, you know those don't need to be there. But if we multiply that out, we get 100 plus 20 plus 3, which is going to equal 123. So the pattern there is that this number here, number 1, we were multiplying by 100, and then the number 2, we were multiplying by tens, and as we moved to the right, we were multiplying the 3 by 1. But if we keep going to the right, beyond the decimal point, that pattern continues. There's actually a decimal point here, next to 123, but we don't write it because in this case there's no useful information beyond it. But if there were, the same pattern would continue. So for example, here I have 0.4, and I can write that as 4 times 1 over 10. Obviously, if I were then to continue that, I could write that as a fraction, which would be 4 over 10. The next example, 0.04. Well, I can write that again as 4 times 1 over 100. Again, that number getting bigger. I'm dividing by another 10 each time. So with each move to the right, we divide by another 10. That means that if we want to, we can actually split up a decimal when we have more information. So for example, here we have 0.456. We can write that as 4 times 1 over 10, plus 5 times 1 over 100, plus 6 times 1 over 1,000. So that's 4 over 10, plus 5 over 100, plus 6 over 1,000. And in that way, we split it into individual fractions. Then what we can do is we can convert them to the same denominator. We did this last week. So in this case, remembering that we have to do the same thing to the top and the bottom of the fraction so that the information remains the same. In this case, to get from 10 to 1,000, we have to multiply by 100. So that's what happens to 4 as well. It becomes 400 over 1,000. 5 over 100, well, that has to be multiplied by 10, top and bottom, to become over 1,000. So it becomes 50 over 1,000. And then 6 out of 1,000 is already out of 1,000. So then we can add those up simply, and we get 456 divided by 1,000. Then, just like last week, we can simplify. Now, you may find that you can go straight from here down to here. And that's okay. Here, if we look at the top number, the 0.456, we can see we are 3 decimal places beyond the decimal point. So you may just be aware that that is 456 divided by 1,000. So that might be the easiest way to convert that into a fraction. But then you still need to simplify like this. Here's some other examples like that. So here I have 0.104. Because I have 3 decimal places beyond the decimal point, that tells me that this is 104 divided by 1,000. Same number of decimal places, same number of zeros after that one. That's the easiest way to remember that. And then again, I have to simplify. So I take it from 104 over 1,000 to 52 over 500 divided by 2. I can divide by 2 again, 26 divided by 250, and then divide by 2 again, takes me to 13 over 125. 13, of course, is a prime number, so we can't go any further than that. But what about when we have zeros? Like this. So here's an example. We have 0.0104. Now, I'm going to use the same technique that I used in the version above. I'm going to count the decimal places. 1, 2, 3, 4. So I'm going to therefore write 0104, everything after that decimal point, which is divided by 10,000 with 4 zeros. Now, again, the smart ones among you may have noticed this 0 isn't doing anything anymore. We don't have a decimal point to keep it after. It's just dead, so we don't need it. So that becomes 104 over 10,000. And again, we simplify and take it down to eventually get 13 over 1,250, and that's our fraction. So there's a couple of different ways you can do it when you're converting a decimal to fraction. You can take each section one by one, convert them to separate fractions, and then convert the denominator to the same and add them up. Or, if you're comfortable with it, you can use the number of decimal places and convert it into an over 1,000, over 10,000, over 10 fraction. And then simplify that. So percentage directly relates to what we've just been doing. Percentage means out of 100, and it means that we can express it either in this way as a percentage, or we can convert that to a fraction per 100. We can also use this to produce a decimal. We divide the percentage by 100 to calculate a fraction or decimal proportion. And then we can also multiply a decimal or a fraction by 100 to calculate a percentage. So here's a simple example. Here we have 12.3%. If I write that as a fraction around that model, I can write 12.3 per 100. If I then calculate that, I get a decimal, which is 0.123. I can do it backwards as well. I could take the decimal, 0.123, and I can convert it to a fraction. Now, I might actually want to do 123 over 1,000. Excuse me while I try and write that. Not the easiest with this. But then that's a really easy fraction to convert into a percentage, because I just knock that off and put a decimal point in there. And that becomes 12.3 over 100. Equally, I can get directly from this decimal here to this percentage here by just multiplying by 100. 0.123 becomes 12.3%. But it's really important you always include the percent figure or the percent symbol with that so that you don't lose information. Otherwise you won't know it's per 100. So here's another example. If I want to calculate 12.5% of 800, there's actually a few different routes that I can use to work it out now. First, I know that 12.5% is the same as 12.5 over 100, and all multiplied by that 800 again. So what do? Well, I could just calculate it with long division, or with my calculator, I can just do that sum and work out that 12.5 divided by 100 is 0.125, multiplied by 800. Then I could calculate that again. But I could also do this. I could say, well, okay, if it's 12.5 divided by 100 times 800, I know that I can just multiply by that number.